Good morning, team. We are ready for video number 2 in our reactions in solution journey. So video 1 was just kind of an overview of how to picture things occurring in water, right? So we got water as this matrix, and we got the solutes moving around, reacting, or not reacting, but it'd be pretty boring if they weren't reacting. We're going to focus on 3 of the big ones in this particular chapter we're looking at. And I'm just kind of summarizing here, and then we'll do a video for each one, although the last one might take more than one, right? And then once I introduce, probably in the middle here somewhere, I'll introduce the different kinds of equations we can use for how to represent these reactions in solution, because there's different ways to look at it that we saw in the last video with electrolytes, right? So we know weak electrolytes and non-electrolytes, the dominant form are those molecules, whereas strong electrolytes, the dominant form is the ions in solution. So that gives us several different ways to represent these species in solution, depending on the information we're after. So we're going to start with the easy one, probably the most famous of all reactions in undergraduate general chemistry and introductory chemistry, and the coolest one, probably one of the biggest reasons I became a chemist, was because of a demo I saw for precipitation reactions. I thought it was the coolest thing in the world, like magic. All right. So here we're forming an insoluble solid, and if you remember, that's one of the driving forces for a chemical reaction to occur. One of the signs, we went through the different signs of a chemical reaction, and formation of a solid from mixing 2 or more solutions together was a distinct sign, because you had a phase change, which means if I didn't have a solid before and I mixed some chemicals, there must have been a rearrangement of atoms to form a new substance that is a solid under these conditions and temperatures and whatnot. So we're going to need our solubility charts for that one, and we'll do that video first, right after this. Then we'll look at neutralization reactions, or acid-base reactions. Harder to see, but also one of the driving forces is the formation of water in this case. And here it's just a proton transfer, as we learned before. We looked at acids are proton donors, bases are proton acceptors or takers. So the acid donates an H plus or a proton to the base, creates some interesting things. Typically, the driving force is the formation of water. You'll see that as a product in almost every single scenario I'd run into. So we'll be able to predict the products. We're going to learn how to predict the products for those 2 reactions following what's called double displacement technique, which you probably have learned before. There's a few exceptions for acid bases. There's some weird ones we'll talk about. Those are the fun ones to do in lab. And then last, and we're going to find some parallels between these 2, very similar. And then last but not least, redox reactions, reduction oxidation. That's a real tough one for a lot of undergraduate students. We will not be able to predict the products for these like we can using simple techniques for precipitation and acid-base reactions. We're going to need some help, something called a redox table. So there's going to be a whole video just on the redox table for this one. But a redox reaction and an acid-base reactions are kind of bizarro twins to each other, whereas neutralization and acid-base reaction is a proton transfer from the acid to the base. Whereas redox reactions, it's an electron transfer, we'll find out, from a reducer to an oxidizer. And the proton's a positive particle, the electron's a negative particle, so it's a little weird to think about redox. But these are the 3 big ones we're going to be looking at, and lots of kinds of reactions fall into these categories. Let's do the first one, a precipitation. Here we go for precipitation reactions. Before we get into the juicy details of some specific ones, let's look at some steps and patterns for how to do these, because this is a little tougher than the last chapter. Last chapter, I gave you the products and made you balance it, or sometimes I balanced it for you. This time, I'm not going to be so nice. I'm not giving you diddly squat. I'll give you the reactants only. So commonly in lab, sometimes you'll only have a name or something like that. And you have to figure out, using what we learned before in prior chapter, how to convert a name to a formula. And so the first thing you want to do, and again, if you did this in lab, you would mix 2 clear colorless solutions, right? And then you would end up getting something that wasn't clear. It was opaque or translucent with little particles. Those particles are impeding light coming through. But that's more of a lab-based thing. So we know we formed a solid upon mixing a few solutions. How do we represent that on paper now with an equation? Write the reactant formulas and their states. Usually that's given to you, right? So if a solution is obviously going to be aqueous. predict, in number 2, we're going to now predict the products. How are we going to do that? Well, we're going to look at what our reactants are, and they're going to be aqueous solutions of ionic salts. Probably have cation, anion for one solution, cation, anion for the other solution. You're going to determine what those ions look like, what are their charges, and then we're going to follow what's called double displacement. We'll do that. You probably learned that in introductory chemistry. You just switch the ions like 2 dancing couples. Woo! Switch partners. There you go. And then you look at the charge ratios of the ions to predict the formula of those products. So once you see how it's done, and I've seen a lot of tricks for that. I've seen people call it the swingers reaction, innie outie, a whole bunch of different things. I don't care how you get it done. Just switch the ions. We'll do a couple examples. Once we determine the product formulas, now determine the product states. Are they aqueous? Are they soluble? Right? Are the products soluble, or are they insoluble? And so we're going to use our solubility chart to determine that. Remember this, right? Soluble comp. So if it's any of these combinations, that would be soluble, or AQ. Any of these combinations, that would be insoluble. We'd put a solid there. Typically, the higher the charges, right? Probably the easiest way to do it is look at your 2 products. The one that contains the ions with the higher charges is almost always going to be your precipitate, your solid. Now, it's possible to get 2 solids. So in lab and homework, you're going to want to have this. Some teachers will give you this on a test. I won't. When I give you them on exams, you'll get 1 solid and 1 that's not. One solid, 1 aqueous. And so typically, you just find the one with the higher charges. You're good to go. Stronger electrostatic forces. Coulomb's law. But in lab and homeworks, always have that with you because there's some weird ones out there. There's some exceptions and whatnot. So always have that to refer to. And that's not a complete table in any way, shape, or form. Once we've got the states, now we've identified everything, got their states. Now we can balance it and obey the law of conservation of mass, right? So always balance the equation last. Do not try to balance the equation up here because you will get confused. Right? The product formulas are determined by the charge ratios only. That might mess up the balancing. That's okay. You'll balance it later. Let's do some examples. Okay, ready, gang? Oh, I wonder why I have these on. Let's see if they work. Home chemistry is a little weirder than lab chemistry. Write the equation. Of course, that's assuming a balanced chemical equation. And we haven't specified the type of equation yet, so we're not worried about things that are strong or weak. We're just doing good old treating them like molecules. We call it a molecular equation. Between 0.1 molar sodium hydroxide solution. Hello. Notice it doesn't give you the formula. No. And 0.1 molar barium nitrate solution. Hello. There we go. So when we do the equations, we're going to have to figure out what the ions are, what their charges are, and what the formulas of the reactants are first. So I already put some barium nitrate in there. All right, clear, colorless. I'll use my glasses case as a background. So now let's add the sodium hydroxide to it and just see what happens. Of course, in lab, we would be recording things properly. Oh, you see that clarity change? So and that clarity is changing because now you can't necessarily see particles looking at it, but that's an indicator that we have formed particles, right? And if we were able to look really, really close into that, I don't know if you can see it, there's little particles floating on there. Yeah, you see those particles in there? We got to precipitate, my friends. Woo-woo! Now, we don't know what that precipitate is. We're going to have to figure that out. So let's go ahead and do that. Let me dispose of my waste properly. See you in a second. While I'm doing this, I want you to see if you can do the balanced chemical equation for that white solid precipitate we formed. Did you do it? Did you do it? All right. This is a pretty straightforward one. Let's figure out remember, we got the steps. First, figure out your reactant formulas. So we've got sodium hydroxide. So sodium is +1. Hydroxide's a -1, right? If you don't know those, you're toast. Barium is a +2. Nitrate's a -1. So identify those ions. I cannot express to you how important it is to have those written down so you can see them. Because in precipitation reactions, we're doing double displacement. The identities of those ions do not change. All they do is switch partners. They are going to retain their identity, so you can't alter that. That's a key factor. So once you see those, we can change the number, the combinations of these, but you can't change what they look like or their charges. So here we go. Let's put these two together. Are you ready? So reactant number 1 has a +1 cation, the sodium ion, and a -1 anion, the hydroxide ion. That's a 1-to-1 ratio, right? They cancel out right on the dot. So that's going to be N. Whoop, let's leave room to balance it. And why did I put AQ there? Because it says solution there. You don't need to. Now you can see it. You can see it's a solution right there. Also, you can see the molarity there. That indicates it's a solution. And I told you it was a solution. So is that enough evidence for you? Any one of those would be fine. We're adding that to the barium nitrate solution. All right? That baby right there. Barium's a +2 cation. Nitrate's a -1. So they don't cancel out. We need 2 nitrate ions to cancel out the barium ion because this is an electrically neutral solution. The charges have to cancel out. So we're going to have 1 barium, and since that's a polyatomic ion, you need to put that in parentheses, yes. Now I'm not going to have enough room here to do this. So I'll put one of my products here and then one of my products there. For you, do it all in one line. All right. Step 1 is done. We have our... Now, sometimes I'll give you those. You're like, thank you, Professor. But sometimes I don't. We've got step 1 done. We've got the reactant, states, and identities. Step 2, let's use double displacement to figure out what our products are going to be. So we've got the 2 ions, right? We've got the 2 sets of ions. So what we're going to do now is just switch them. All right, so I used them to form my compounds. Now, if you want to write them over again, I'm going to erase those and do it over again and show you how we switch them. Yeah, it's not too tough, but let me bring that below so you can see it a little better. Let me erase this. Now that we have those, I'm going to write them down below. So we've got the Na+, OH-, so think of that as like a dancing couple, if you're into those soda shows. We've got the barium. I just have a little more room down below, so I'm going to do that. Now, let's do our double displacement. So we'll just switch. We'll just switch. You ready? Now, would you agree the 2 cations are not going to go together? And the 2 anions are not going together. So when I pour these 2 solutions together, these are both soluble, so they're strong electrolytes, so they actually exist. In here, the barium ions are moving around separately from the nitrate ions. In this one, the sodium ions are moving around separately from the hydroxide ions. They're floating around separately. When I put them together in that test tube, now I have all 4 ions moving around, so I have several combinations, right? So obviously the sodium and hydroxide aren't going to combine because that's the starting thing. The barium and nitrate aren't going to combine. That was the starting thing. The sodium and the barium aren't going to combine. They're both cations. The hydroxide and the nitrate are not going to combine. They're both anions. So the only possible combinations would be the cation of the first species and the nitrate of the second. Wah, wah. And then the anion from the first one and the cation from the second one. Wah. That's why you hear some people, well, mostly just me, call it the innie-outie. The inner ones go together, the cation of that one, the anion of that one, and then the outer one's the anion of that one, and the cation of that one. Innie-outie, right? Or you can think of it as dancing couples where they just switch. Do-si-do, whatever you want. There's a show called Swingers, if you're into that one, you know, those work. Whatever it takes to get it, you're good to go. Now, let's combine those. Sodium's a +1. That's going to combine with a nitrate, which is a -1. Same but opposite. So that's a 1-to-1 ratio. Everybody agree? So we're going to get NaNO3. Now we don't know what that state's going to be. We'll do that in step 3. What's our second product going to be? So we got this one. Check. Now, always do cations first, right? So the barium's a +2, the hydroxide's a -1. So we need 2 hydroxides. Remember, we're looking at double displacement and the ion charge ratios. Doesn't matter how many you have here. That's irrelevant. So it'll take 2 hydroxide ions to cancel out 1 barium. So when I have a barium, that will require 2 hydroxides. But I only have 1 there. Remember, balance it last. Don't worry about that. Balance it last. We'll take care of that later. That's how you determine the product formulas. Now we got to figure out if those are going to be soluble or insoluble solids, and that's where we get our trusty solubility chart from. Now, if my life depended on it, I couldn't look at anything, I would predict the one with the higher charge. See, the barium's the higher charge. I would predict that one. I would predict that one. All right, let's confirm it. Let's look at our solubility chart. Do you see the sodium in the alkali metals? Those are soluble. Sodium doesn't like to form precipitates, and there's no exceptions. So if you ever see sodium or nitrate, right? You see nitrate. I also put nitrite there. There's no exceptions. So there's no way that could be a solid. There's just no way. Let's look at I don't see barium on here, but I do see hydroxides. Right? You see where it says most metal hydroxides and oxides? Those are insoluble. So hydroxides are tiny. Even though they're -1, they're tiny. They love to form precipitates. There's a few exceptions, the ammonium ion or alkali metals. So that's why sodium hydroxide's not. But that's an alkaline earth metal. So we predict this to be a solid. An insoluble solid, and that's a soluble salt. We'll put AQ. That's how you predict those. Right? And I really didn't need that chart. I just said, well, higher charge, I'm pretty good there. But sometimes you can get 2 precipitates. That can be a little weird. All right? But on my exam, that will work. So that was step 3. Right? Step 1, get these formulas. Step 2, get those formulas. Step 3, let's get the phases. Now we can balance it. Yes. Here we go. You ready? 1 sodium, 1 sodium. 1 barium, 1 barium. I like to do the metals first. Now, the polyatomic ions have not changed identities. You don't have to do it by atom. You don't have to do the oxygens and the nitrogens and stuff. You can do it as the hydroxides and the nitrates. It's easier that way. Do you see how you've got 2 nitrates here, but only 1 nitrate there? So we need to put a 2 here to get the 2 nitrates. And you see the 2 hydroxides there, and we only have 1 hydroxide there. Or you can say, well, that screwed up my sodiums. I now have 2 sodiums, so I need to put a 2 there. So that gives me 2 sodium ions, 2 sodium ions, 2 hydroxide ions, 2 hydroxide ions, 1 barium ion, 1 barium ion, and 2 nitrate ions, 2 nitrate ions. That's your last step, always. That's how you do the molecular equation for a precipitation reaction. Yes. All right, let's do one more. It's a little more challenging. All right, here's your task, my friends. Write the equation for the reaction between gadolinium 3 acetate, solution, and potassium sulfide solution. I am not going to demo this one because I don't have gadolinium solutions. Right, that's down there with these crazy lanthanides and actinides, right? So that's a lanthanide. See gadolinium right there? Woo! I don't have any of these laying around in my house. Not that I'd even want to. But we'll have some fun theoretically with this one. Assuming we could do this. So pause it. Determine. Now, I was nice and I gave you the formulas this time. Thank you. Thank you very much. Thank you very much. Predict your products. Doing the double displacement of the charge ratios. Predict the states using the solubility table or solubility chart. And then balance it. 1, 2, 3, go! I don't need to pause it. Let's just do it. So I'm going to write these down. I've got, I'm just going to rewrite these. So here's my gadolinium 3 acetate. How do I know it's gadolinium 3? Because acetate, you should have memorized by now, is a -1 charge. And there's 3 of them, so there's only one of those. It must be a +3. And I'm going to mix that with potassium sulfide. I know they're aqueous because I said they're solutions, right? I don't need it. The solubility table is for products, right? Use that for products only, okay? Let's do our little arrow going through. Identify your ions. You ready? If you can do it in your head, great, but I recommend you do this. Gadolinium is a +3. Acetate is a -1. Right? If you're struggling with that, have your polyatomic ion chart with you. Potassium, you should know, is a +1. And there's 2 of them. So the sulfide ion's a -2. Highly, highly, highly recommend you do that every single time. Now let's do our double displacement. Innie, outie, swingers reaction, whatever you got to do. And these 2 are going to go together. So I'm going to get potassium acetate, innie, outie. So let's write that down. Potassium's a +1. Do the cations first. Acetate's a -1. So they go together in a nice 1-to-1 ratio. So I'm going to go KC2H3O2. I do not know the state yet. I'm going to look that up. That'll be step 3. Let's do our outer ones. We've got gadolinium 3 with sulfide. Now, they are not equal and opposite, right? 3 and 2 are not the same thing, so they're not going to go in a 1-to-1 ratio. Gadolinium's a +3, sulfide's a -2. One's odd, one's even, so we need to find, they're not going to go in nice even multiples there. We got to find the least common multiple, so 3, 2 would be 6, correct? So to get to 6, I need 2 gadoliniums, and to get to, so that's for a +6. To get to a -6, I need 3 sulfides. So -6 and +6 would give me a net 0. So I need 2 gadoliniums, gadolinium 3, and 3 of the sulfides. And that is the ratio it has to be to give me a neutral compound. Gadolinium 3 sulfide. Now, if your life depended on it, you couldn't use a solubility chart, which one would you predict was the solid? Well, that's a +1 -1. That's a +3 -2. Which has the stronger electrostatic charges? I would predict that to be my solid. If this was a test and I'm moving as fast as I can do that in 2 seconds, right? Let's confirm it on our solubility chart. Do you see potassium right there, baby? Or any alkali metals in my class? They're never going to form precipitate. You see acetate right there? They never form precipitate. So that's about as soluble as soluble is going to get. Gadolinium, I don't see on here anywhere. But I do see sulfides there. See the sulfides? They really love to form precipitates. There's a few exceptions, the ammonium ion and alkali metals, which gadolinium is not. So that this predicts that gadolinium 3 sulfide is going to be an insoluble solid. Bingo! Step 1, product. Step 2. Step 1, I'm pointing at the reactant. Step 1, reactant formulas, which I gave to you. Step 2, double displacement and ion charge ratios. Get me the product formula. Step 3, get me the states using the solubility chart. Same thing every time, guys. What I mean, you get to the test, if you've done this enough, you just, step 1, do this. Step 2, do that. Step 3, do that. Step 4, do that. Step 1, do this. It's the same thing. So you just like this machine on a test, just like in sports. Somebody hits the ball, bam, 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 right? It's automatic, right? Do you think, pro basketball players are thinking about the technique when they're shooting? They're not, right? It's automatic. They've done this hundreds of 1,000 times probably. Let's balance it. You ready? That's the last step. I always do the metals first. I like to start with the cations personally. 1 gadolinium, 2 gadoliniums. No! Which means I need to put a 2 here. So I got 2 gadolinium cations right there. Acetate looks a little scary. Let's look at the potassiums. I got 2 here, so let's put a 2 there. Let's look at the sulfide, because the acetate's scary. It scared me. I got 1 sulfide there, but I got 3 here. So I need to put a 3 there to balance the sulfides. Oh no, that screwed up my potassiums. So now this gets messed up. So let's erase this. And we need 6, right? So let's erase that and put a 6 there. So I still have 2 gadoliniums, 3 sulfides. 2 times 3 is 6 potassiums. 6 times 1 is 6 potassiums. That gives me 6 Acetates, 2 times 3. The last one always works out. Isn't that nice? It's the same thing over and over and over, guys. I can't make it any harder than this. Follow it. Step 1, reactants. Step 2, double displacement, ion charge ratios, product. Step 3, use the solubility chart to predict solids or aqueous, whether they're soluble or insoluble, and you probably don't even need the chart to do it. Step 4, balance. Done. Boom, boom, boom! You got it.